Alright, so in this video I'm going to be explaining another important article with the title Representation Learning and Graphs with Jumping Knowledge Networks. This ICML paper in 2018 that we always now use this idea of jumping in all our PyTorch geometry code if you want to do the traditional K-layer graph neural networks. So recent deep learning approaches for representation, learning and graphs follow a neighborhood aggregation procedure. We analyze some important properties of these models and propose a strategy to overcome those. In particular, the range of neighboring nodes that a node's representation draws from strongly depends on the graph structure analogous to the spread of a random walk. To adapt to local neighborhood properties and tasks, we explore an architecture jumping knowledge networks that flexibly leverage for each node different neighborhood ranges to enable better structure-aware representation. In a number of experiments in social bioinformatics and citation networks, we demonstrate that our model achieves state-of-the-art. So we summarize this sensitivity analysis by what we name the influence distribution of a node. That this effective range implicitly encodes prior assumptions on what are the nearest neighbors that the node should draw information from. We will see that this influence is heavily affected by the graph structure, raising the question whether one size fits all in particular in graphs whose subgraphs have varying properties. So we raise a question whether it is possible to adaptively adjust or learn the influence of radii for each node and task. To achieve this, we explored an architecture that learns to selectively exploit information from neighborhoods of different locality. This architecture selectively combines different aggregations at the last layer. For example, the representations jump to the last layer. Hence, we name the resulting networks jumping knowledge networks. You see the expansion of random walks starting at the square nodes in subgraph with different structure. Different subgraph structures result in very different neighborhood sizes. So we do aggregation and update, and you are familiar with GCN and graph attention and all of these things. But how about a skip connection? Because in traditional graph neural network, you only have aggregation and combine, nothing more. So if we skip a layer or use a certain combine, all subsequent units using representation will be using the skip implicitly. For example, graph attention learns to select the important neighbors via an attention mechanism. So this model can also be combined with graph attention. So they defined what is influence score. Of course, I have a playlist about influence maximization. That's a different story. But in this context, they defined the influence score I of X and Y of node X by any node Y is the sum of the absolute values of the entries of the Jacobian matrix. Of course, calculations of all of these pairs are very high, the complexity is high. So we need to see what is the novelty of their paper. Consider a random walk starting at node V0. If at the tth step we are at node Vt, we move to any neighbor of V sub t with equal probability. So the influence distribution for different aggregation models and nodes can give insights into information captured by respective representations. The following results show that the influence distribution of common aggregation schemes are closely connected to random walk distributions, with the randomization assumption of ReLU equation similar to that in this paper. Also in this paper, we can draw connection between graph convolutional networks and random walks like this, that given a k-layer with average as in equation 3, with averaging like that, then assuming number 3 is here. So here we are using this averaging like here for a simple averaging for aggregation. Now the theorem saying that given a k-layer with that averaging, assume that all paths in the computation graph are activated with the same probability of success rho, then the influence distribution I sub x for any node is equivalent to the k-step random walk distribution on G tilde starting at node x. So the big picture is this. This is a 4-layer jumping knowledge network. As you see, we jump to the last layer from all layers. We jump. And to better understand the implication of theorem 1, this one that we said, and the limitations of the corresponding neighborhood aggregation, we revisit the scenario of learning on social networks. Random walks starting inside the expander converge rapidly. Of course, expander is fantastic. I've explained many videos about expanders on my playlist on approximation algorithm. It's a classical challenge in computer science. But an expander is great because you don't have problem of over squashing or under reaching on that, because quickly with very few hops, very few walks, you can go from one node to another node. And that's why it is fundamentally is very important, this kind of graph, expander graphs. So some papers just create algorithm to create an expander graph. They do it for rewiring purposes to avoid over squashing, under reaching. They do it for many reasons, even to avoid over smoothing. So then we concatenate. Here is very straightforward. And if the transformation weights are shared across graph nodes, this approach is not node adaptive. I know you can also use max pooling, LSTM attention, concatenation. So there are 3 things. The second one is max pooling. The third idea is LSTM attention. Any of them is fine. So JKNet learns to adapt. The key idea of the design of layer aggregation function is to determine the importance of a node subgraph features at different ranges after looking at the learned features on all layers, rather than to optimize and fix the same weights for all nodes. Under the same assumption, we show below that the layer-wise max pooling implicitly learns the influence locality adaptively for different nodes. So they did an experiment for these data sets like Sightseer, Quora, Reddit, and PPI. Nowadays, we have high accuracy for all of them, especially PPI, which I got 90% validation, 95% for training. It's very simple. So all of these are not challenged anymore. The next generation, the next research problem is you should work on heterophilous graph, because these high homophilic graphs, you can get high accuracy for many reasons, and even an MLP can do. But for node classification, but for heterophilous graph, you need both of each node. You can use. Some people use a combination of multi-layer perceptron and graph neural net, because GNN captures the locality, but MLP cares about the attributes of individual nodes. But the heterophilia problem is that you cannot do just the traditional graph neural networks, or you should create many innovations in order to get a high accuracy, especially for data sets like Squirrel and Chameleon. These two data sets, state of the art is less than 50%. It's amazing. We are in 2026 and we think we are something, but still state of the art is 50%, even for these simple benchmarks. So now you understand how hard it is to design human brain, because even for simple data sets, we cannot do a simple task. A simple isolated task, we cannot do that. So that's why I don't understand why human is so proud